Hello, everyone. Welcome to Character Generation, Game World Building with Recurrent Neural Networks. I'm super excited to have y'all back. This is part 2 of a 3-part series. I hope you're having a great Global Hack Week so far. I know we're getting towards the end. So I'm just going to kind of dive right in and pick back up where we left off yesterday. So today we'll be moving on a little bit more with the model that we built yesterday, integrating some more data, and I'll also be giving more of an overview of some of those recurrent neural networks topics we talked about yesterday. But if you're just diving in now, maybe you didn't catch part 1. My name is Gabriella. I'm a coach here at Major League Hacking. I've been with Major League Hacking for about a year now. I'm very enthusiastic about machine learning as well as Candy Crush. And I also want to call out that if you're just joining and you haven't had a chance to register your attendance at Global Hack Week, make sure you do so. I have a link up on the screen, and I also send it in the chat. And this is your way to gain more progress towards swag through Global Hack Week. I'll leave it up on the screen for a second, so you'll have a chance to register your attendance really quickly. All right. I think that was enough of a chance, but if you missed it on screen, you're more than welcome to use the link in the chat to register your attendance for today's session. So here's a little bit of an overview and agenda of what we'll be covering today. First, I'm going to dive into gated recurrent units. Yesterday, we used gated recurrent units to build out our model. I'll be diving a little bit more into kind of like the concepts behind that. We'll also be talking about long short-term memory, which is another concept in recurrent neural networks. And we'll be diving into that a little bit more as we build out our character age generation model today. And after we go through those concepts, we talk a little bit more about the conceptual aspects of what we'll be doing later today. We're going to start by integrating a larger data set into the part 1 model we built yesterday. If you remember at the end, I had found a baby names data set from Kaggle. So we're going to be integrating that into our model and see how much better the model gets with more data. If you remember yesterday, we just had kind of like a list of a bunch of different names. So it wasn't going to be as comprehensive or have like enough data to kind of like generate a wide variety of names. So I'm excited to kind of integrate that in there, and we can see how it changes like with that additional data. So after we kind of fine tune yesterday's model, we'll be working in diving into a few new models with some new concepts we learned today. We'll be building out an age model with long short-term memory. We'll also be starting our appearance generation with GRUs. This is essentially we'll be generating different characteristics of our character's appearance, such as we have our age already and their name, but we want to know like things like what color is their hair, like what kind of hair do they have? Do they have curly hair? They have straight hair? Something in between. A little bit about like the types of clothes they wear, and then we'll be feeding those kind of like appearance characteristics into the OpenAI API, so we can actually generate images of our characters using DALL-E. Hopefully we'll be able to get all that done during part 2 today, but if not, we can have a little bit of overflow into part 3 this evening, which will be happening at 7 p.m. Eastern. It's all on the Global Hack Week schedule, but without further ado, it's time to kind of get back into some of the concepts that we talked about yesterday and build a little bit more upon them before we dive more into coding. So kind of as like a brief overview of neural networks, we talked a lot about neural networks yesterday. Neural networks are kind of like an interconnected group of nodes. They're modeled after a simplified version of our brain's neurons. And essentially, they're connected by edges where nodes send signals from one node to another. The hidden layer nodes perform different transformations on the data. And once that data has been processed, the new data is sent as a signal to the output. And they all receive different weights for like the amount of information they have. So that is kind of like processed and factored into the information that is gathered in the output nodes and will essentially lead to that output information. The nodes are aggregated into different layers like input, hidden, output. They're used for a variety of things like predictive modeling, adaptive control, and they can learn from their experience and derive conclusions from complex and like seemingly unrelated sets of information. If you want to know more about neural networks, you can tune into yesterday's stream, but I just wanted to give a brief kind of recap of what we talked about yesterday. Nodes are like neurons in our brain. They're interconnected and process information in a very complex way to find different solutions and different conclusions. A little bit of an overview of recurrent neural networks. So essentially, recurrent neural networks are designed for sequential data processing. You can see an image that kind of shows you what recurrent neural networks look like. They're very similar to normal neural networks, except they have recurrence going on during the hidden layer, which makes them a deep learning network. And they are solving a very pressing problem with traditional neural networks, is that traditional neural networks have no memory of what happened in the past, but because of how RNNs run, they have a memory of both the input data as well as the signals that are being sent. So they have more context and are able to come up with like more complex solutions and complex conclusions as well. That's RNNs. That's what we'll be focusing on for the rest of this workshop. That's kind of a brief overview. Like we talked about yesterday, there are a bunch of different types of RNNs. We'll be focusing on long short-term memory, as well as gated recurrent units. I'll be diving a little bit more into both those concepts in just a little bit. And just to refresh, some of the applications of recurrent neural networks are NLP, as well as time series analysis and player action prediction, which is the most relevant to our game, like Global Hack Week game stream this week. All right, so now here is the new material, now that I've given a brief recap of all the information we covered in the conceptual part of yesterday. So now it's time to dive into long short-term memory, which is a specific type of recurrent neural networks and what we'll be using today to generate our characters' ages. So essentially, recurrent neural networks, essentially long short-term memory, are recurrent neural networks that solve the vanishing gradient problem in traditional recurrent neural networks. If you, like I was originally, are unfamiliar with the vanishing gradient problem in traditional recurrent neural networks, this is kind of like a brief overview. The vanishing gradient problem is when during each iteration of like traditional training in neural networks, weights receive an update to the weight. We talked about this yesterday, how as the process occurs, the neural network will begin to learn how each neuron and each signal needs to be weighted in order for them, like the weight and the conclusions to have a conclusion that makes sense, because they're weighted in a way that's proportional to how much it actually affects the problem, the network. This is a good thing because it does automatically update. We're kind of solving issues by updating the weight and making sure that it's not just an initial arbitrary one, but one that makes more sense. But when we do receive updates to these weights, this increases the sequence length and causes the gradient magnitude to grow uncontrollably, which will slow the training process, which can cause model training and model building to take a very long time. If you're working with a very large set of data, you'll see this if you're just using like a traditional recurrent neural network. As the training goes on, it'll take longer and longer to go through a process where you're inputting data into one side and having it output the data throughout the recurrent neural network. It becomes like the processing load just grows a little bit uncontrollably, especially with large data sets. So that needs to be controlled somehow. And long short-term memory essentially solves that. So an LSTM is made up of a unit, and inside of that unit, you'll have a cell, an input gate, an output gate, and a forget gate. So this kind of just like sounds familiar to you. That's because there are input and output in our traditional recurrent neural networks. As you can see here, we have the input and the output in our recurrent neural networks. It's pretty similar to long short-term memory, as long short-term memory is a type of recurrent neural network. It's just a little bit more memory efficient and will allow us to adjust the weighting of different aspects without slowing down that training process. All right. So now that we've kind of like talked about what LSTMs are composed of, I'm going to give you a little bit of an overview of each of these individual parts. So a cell is what remembers the values over arbitrary time intervals, and as well as the three gates that regulate the flow of information in and out of the cell. This is remembering all of the specific time intervals. This is very important for time series analysis, but it also regulates the flow of information in and out of the cell, which is important to make sure that we are keeping our training process kind of like at a reasonable level, because it's not allowing too much to be outputted or too much information to be taken in. And then we have the forget gates. This is the very important part of long short-term memory, because it's what is determining what we need to forget, and it's not holding on to all this information that in traditional recurrent neural networks will slow down that training process. So the forget gates are essentially doing the heavy lifting to allow long short-term memory to actually function in a way that isn't as slowed down as traditional recurrent neural networks. So it decides which information to remember and which to discard. And it does this by comparing previous states to the current state and seeing how valuable the previous state is in the context of what it knows. And it assigns a value between 0 and 1 based on how important this information is. So a value that is rounded up to 1 means it needs to keep the information, and a value of 0 means to discard it. So it'll be assigned a value of 0 to 1. And if it's assigned a value of like 0.2, it's less important. So we'll be more likely to discard it. And if it's rounded up to 1, so if it's like 0.7, that means that the information is important and needs to be kept. As information is not quite a 0, but a little bit lower on that 0 to 1 scale, it won't necessarily be discarded, but will kind of like as it goes through the iterations of training the model, if that value becomes lower, it will likely go from a 0.2 down to 0.1, 0.05, and eventually down to 0, where it will get discarded. Or if we find later on the iterations that that piece of information is actually important and the 0.2 is raising in value, and it means we need to keep it, then it will be kept. And as far as the other two parts of the LSTM unit, we have input gates and output gates. So the input gates are deciding which pieces of new information to store in the current state. It uses the same system as forget gates. So after forget gates have processed through information, we're doing this again when we're inputting new information into our current state. So we'll assign something, it will assign a piece of information, a value of 0 to 1, and it will decide which information we're going to store in the current state rather than discarding it. Like I said, with recurrent neural networks, it has memories of both the input as well as the signals that are being sent. So in input gates, we're deciding which specific information is necessary, which inputs are key from previous rounds to be kept in the current state. Whereas forget gates are comparing things a little bit more broadly and using both previous and current states of information. And the output gates are doing something similar, but they're controlling a piece of information in the current state that they want to output. They're also using the 0 to 1 system, but in this particular instance, they're comparing both the previous and the current states, and the ones that aren't deemed as important and they need to keep the information aren't outputted to the next neuron. And the key benefit of being selective and ranking everything is that it allows the LSTM network to maintain a very efficient flow. The training process isn't taking forever, which with RNNs, if you don't program it in an efficient way, you're giving it very large data sets. It can take a very long time as the weighting increases, the magnitude and the memory of this model. But being very selective with output and the LSTM networks allows for all the dependencies to be useful to making predictions, and we're not including unnecessary context that won't actually add anything to our conclusion or our decision, but rather it's just like taking up space and wasting time when we're trying to train our model. All right, so that was a good amount of information. All right. Someone asked, is this right that transformers are evolved recurrent neural networks? I believe so. I have not personally worked with transformers, so I will look into that during our break between part 2 and part 3 and get back onto you, but that sounds familiar. So I believe that is the case. Doesn't look like we have any other questions. A few lettuce emojis, which is very popular this Global Hack Week. And I also wanted to call out the link up at the top. It says MLM Gentle Introduction to Long Short-Term Memory. It's not a multi-level marketing scheme. In fact, it's just a little bit more of a deeper introduction into long short-term memory. I'll share my screen and we can kind of walk through this a little bit as well. Let me switch my screen and then I'm going to scroll all the way to the top. Looks like there's some ads at the bottom of this article. But essentially, MLM stands for Machine Learning Mastery, not multi-level marketing scheme. It's written by Jason, who studies machine learning, has like a PhD in computer science, I believe. Actually, read more. Oh, artificial intelligence specifically. Okay, awesome. So I like his articles because they are thorough, but aren't very confusing or needlessly complicated. There's also a little bit of like, there's like quotes to support everything. So if outside of like the basic explanation, you want to learn more, the quotes are a good way to kind of like piece things together. And there are images occasionally that kind of go along with the concepts. There's a lot of like tutorials as well. This is just kind of like an introduction to long short-term memory on like a broader scale outside of just like a single slide. And I think that the blog overall of like machine learning mastery is a really cool resource if you're looking to learn more about machine learning. All right. So let's switch back to the slides. Excuse me. Coming down with a little cold, I think, soon. All right. So here is a little bit more about long short-term memory. Here is a diagram of long short-term memory. The top one has a little bit more of everything simplified with like the mathematical equations. If you're really into the math behind machine learning, I think like that's a good place to look. But if you're more just interested in machine learning and learning about long short-term memory as a concept rather than like a specific, like the specific equations behind it, the larger diagram is a little bit more of what you would be looking for. So as you can see, we have our forget gates, the input gates, output gates, as well as our memory. So the memory is just kind of like this, like also known as the cell. It just will change between like different sources like to call it different things. And as we can see here, our memory is relatively constant. It's slightly increasing towards the end. And we have our information like flowing from the forget gate and then up to the memory. Before we go down to the input gate, we're getting more information. It's going into our candidate memory. And our output gate is discarding or outputting information. So this is kind of like the overall flow of long and short-term memory. And then also there's a link, I double linked the MLM Gentle Introduction to long short-term memory, but there's also the intuitive explanation to long short-term memory. That's where the bottom diagram is from. And that's also a really good explanation of long short-term memory. If you need a little bit more resources or maybe want to hear it described in a different way, I think that's a great way to kind of integrate like your learning from like different sources and hear it explain in different ways if like that's something you need or are looking to do. All right. So now a little bit more about gated recurrent units before we dive into actually coding today. All right. So gated recurrent units are what we used to develop our model yesterday. If you weren't here yesterday, we created a model to generate different characters' names. Gated recurrent units are similar to long-term, short-term memory. They just have less parameters. So I like a similar gating mechanism for how they flow information throughout the model. It just has less parameters and it doesn't have an output gate. So it's not filtering information before output, it's just filtering it throughout the input and processing part. So there's like not as many parameters as LSTM. They're just like not quite as complex, but they do have similar performance and also reduce kind of like the memory and processing time that we'll see in traditional recurrent neural networks. For example, like in when comparing gated recurrent units performance to the performance of long short-term models in polyphonic music modeling, speech signal modeling, and natural language processing, the performance was pretty similar, if not identical, and it's not as quite as complex for building out and managing. These are also a good solution. Here on the left, we have kind of like the mathematical diagram for gated recurrent units. I'm not going to dive too deep into that just because we're focusing on the technical applications. But if you're curious to learn more about the math behind gated recurrent units, I did encourage you to do so. So that's a little bit about gated recurrent units. If you want to learn more about gated recurrent units, I also have an article linked up at the top. It's called Understanding Gated Recurrent Units. It looks like it's slightly blocked by the Global Hack Week logo on the screen, but after you get the slides post stream, you'll be able to access this link. It's from a source called Towards Data Science. I really love Towards Data Science because they break everything down in a really easy to understand ways. They have both kind of conceptual explanations, the mathematical explanations, as well as technical tutorials, which I really enjoy watching to kind of like improve your understanding. They have a lot of pretty far in career data scientists who are writing out these articles or these tutorials, which I think is pretty useful, especially as someone who is just kind of getting into the world of data science and machine learning. All right, so now that we've gone through a little bit more of an explanation of recurrent neural networks, I've given a little bit of a recap as well as long short-term memory. We're going to dive into a little bit of coding. I do want to call attention, though, in long short-term memory before we get into coding. Some concepts that long short-term memory is focused on are classification, processing, and predicting data based on time series information, which makes sense because they have such a focus on the time in long short-term memory. And some of the applications that you can see long short-term memory being applied into are identifying handwriting, speech recognition, machine translation. So think of machines that are able to translate information or languages from one to the other, speech activity detection, robot control, and also they're frequently used in video game sequencing and in healthcare for some of the more complex problems, such as gene sequencing or kind of like disease detection as well. I forgot to bring that in whenever I was explaining LSTM as a concept, so I just wanted to call that out before we move into the coding aspect of this stream. So this is where you're able to find the code that we worked on yesterday. I'll give y'all a brief overview of the code we worked on yesterday, but it just goes to GitHub repository. I'll be opening up the code in GitHub Codespaces, which is a browser version of VS Code. So give me 1 second to switch over my screen, and then we can get started with coding. All right. All right. I've shared my screen. Here is GitHub code spaces. I will put the bit.ly link in the chat if you'd like to go access the repository yourself. It's a public repository for anyone, but if you're not able to follow along with me directly, you're also able to access this code after the fact. I'll be pushing part 2 after the stream is over. So I'm going to quickly bring this over into the chat. If you'd like to follow along or code along with me, you can do so by cloning that and bring it into your local machine. So as a brief kind of recap of what we did yesterday, we started off by importing a bunch of different things. NumPy, Pandas, TensorFlow. NumPy and Pandas are different libraries that you can use for processing data and also different operations for altering or translating your data. TensorFlow is a machine learning library. So they have a lot of pre-built in functions and aspects to models. So here, this line that is from TensorFlow Keras layers has different functions we used in our recurrent neural network yesterday. And then here we have a padding sequence function we used yesterday, as well as a 2-categorical function we used yesterday. So we started off by defining our sample names / our data. So you can see it's just a list in Python, not too many names. So today we're going to start off by integrating some more names. After that, we created a vocabulary based on these sample names. And then we converted our character names into sequences. And after we made our character names into sequences, you can see here it's a nested for loop where each name is a sequence of the characters that make up a name. So each name, for example, Quinn would be a sequence, as well as Patrick, and each individual character would make up the sequence of the name Quinn. So something like Q, U, I, and N, for example, but I'm going to Control Z so it's back to a normal name. Then we padded our names. We padded our names in the sequences to ensure that our names had an equal length later, and it wasn't confusing our model. So we went through and used some of those pre-built functions we imported from TensorFlow. And then we created both our X and Y input and target sequences by splicing our padded sequences variable, which is those different names that are in sequences. And then right here, what we did was we checked the shape of both our input and our target sequence to make sure they were equal and we weren't going to have any data incompatibility errors later. And then here, we converted our target sequence into one-hot encoding. This just makes it, utilizing it with our model a little bit easier because it's already in the categorical encoding that we needed it for. After that, we defined a few characteristics for our gated recurrent units based character generation model. That's quite the mouthful. So we defined both the vocabulary length as well as our embedding size. I forget what exactly the embedding dim variable name stands for. So I'm going to have Copilot explain this variable name to me again. Okay, the embedding dim variable represents the size of the vector space in which the words will be embedded. Okay, so this is just kind of, we're focusing in on the vector size of the words that we're embedding later in our characteristics. It could be 32 or 100 or larger. We'll probably use a larger variable when we import all of those data those names in the data set later. But for our list, this was more than sufficient. All right, so after that, we actually created the model. We were running into some issues with the original code I had come up with preparing for this stream. Originally, in, I believe it was the embedding, the embedding function, we initially had input length is equal to max length minus 1. We tried it with both max length max name length -1, as well as just max name length as a variable. Both of those it was not like recognizing, and the return statement said it did not recognize the variable, or that the variable wasn't a valid integer. But when we went to go print out the value type, it did return integer. I didn't come up with any solutions as far as that overnight, but whenever we were going through and building our function, we learned that we didn't actually need this variable to run the model, so we went ahead without it, and I think it turned out relatively fine without that. Here we have our model. We have the embedding function, our gated recurrent units function, as well as the dense function. We're just declaring a bunch of different aspects of our model, including how many vectors we want the input to be, how many vectors we want the output to be, as well as the gated recurrence units. We're setting it equal to 128 for our first variable, which I'm forgetting the variables as well. So let's ask for each of the variables it's asking for, and I'll know a little bit more about what we put in there yesterday. And then followed by the gated recurrent units function, we also have the dense function as well. All right, 128 units. Okay, so it's each of the gated units. Okay, that makes sense. And then it's returning the sequences, so it's going to output the hidden state each time, not just the last one. Okay. And then we have the size of our vocabulary, the number of output units in the dense layer, and activation means that softmax activation is used for this layer, and it's used for multi-class classification and output probability. Okay, this is what we used for our probability that we used later in the sequence to actually output those names. Awesome. I'm gonna look and see if we have any questions so far. No questions. Someone just is excited by GitHub Explain. I also love that function. I love Copilot. So here we have us compiling the model. We're just using the atom optimizer, as well as we're using categorical cross entropy as our last variable. And finally, we're actually training that model with our input and output variables. We set 50 epochs, and verbose is equal to 1. 50 epochs is all of these things we're going to see kind of being outputted here, as well as the loss that we're seeing being outputted as well. Looks like everything is running pretty well. So here's where we actually called our function. After we created it, we compiled it, and we trained our model. We declared a seed character. So essentially what this does is this is the first letter that our name will start with. We're going to map all of our seed characters to a specific index. And here we're actually calling our model. The higher the temperature, that is the higher the randomness of an output will be. So the more random a name will be. We found that it was creating more like realistic names when we increase the temperature, because it was diversifying the letters a little bit more rather than having like 4 A's in a name that was like 5 characters long. It wasn't super realistic. It occasionally might happen, but we weren't getting a great diversity of names. Here, we're using the probability to actually call our function and generate random characters based on like what we trained the model on. And the vocabulary, we're determining our next character with the random function, adding it to our seed, which is like what our name will end up being. And then we're adding that particular character to our seed index, so that when this for loop runs again to determine our next character in our randomly generated name, it's actually going to be printing out. So we can see our last name was WRLH. Now we're getting an error. Char to index is not. Oh, I think it's because I haven't run these since I was in this instance of Codespaces. So you learn something new every day. All right, that's all been installed. Perfect. Now it's time to actually create our model. All looking good. I'm going to declare our seed winner. Perfect. We have another name. All right, I'm going to change this to be CH. All right. Click in. Scan. All right, cool. So now I've done a brief explanation of what we did yesterday, what our code is doing. Now I'm going to input our national names.csv. This is a data set I found yesterday on Kaggle. It's a very large file. I tried to upload or push the state names as well. After I got off stream, I was doing some merge conflicts, as you may remember, but the state name file was just too large of a data file to even push to GitHub. So I'm going to try Rainbow CSV, see what the extension looks like. Can maybe close this and open it again, see what the CVF Rainbow CSV actually does. Open anyway. It's thinking. It's a very large data file. So these are just essentially popular American baby names from the 1880s through, let me look at what it says in the data set explanation. nationalnames.csv, the year, it's loading, descending. Looks like the most recent year was 2014, so it takes baby names in America and how many times babies were named a particular name from the 1880s through 2014. So quite a wide variety of names. So here we have in our data set, you can see the ID of each individual item. That's not super necessary as a variable. We have our name, which year it was popular, as well as the gender of that baby and the count of this particular name. So I think that if we kind of like weight the name evenly with our particular name, so the name as well as the count will be easy. One thing I do want to do is combine names over the course of a year. I want to have it so we have maybe the count of Mary from 1880 to 2014 rather than every single year. I think that will make our data set a little bit more manageable. And I think that's kind of like the first step to kind of like start cleaning our data so we can actually integrate it into our model. So I'm going to go through and I'm going to make a copy of part 1 of the Python file. And I'm going to rename this to part 2. This is everything we'll be doing today. Part 2 IPython file. And this is where we're going to go through and run everything. Before we get started with coding today, we're going to have a brief intermission. So for 2-ish minutes, feel free to run, grab some water, some tea, head to the restroom, or even just stretch. And you can also get set up with the code repository. So I'll be back in about 2 minutes and we can dive into coding for today. So we're taking a brief intermission. I'll see you on with you. All right, I'm back, y'all. Intermission is over. Hope y'all were able to grab some water or stretch a little bit. Let's see if we have any questions before I get started. Someone asked, do I add the names to my code? That's what we'll be doing together. Is adding the CSV to our code and updating that model. So just kind of follow along. The link to the code I pushed yesterday is up in the repo. You should have access to the CSV. If you'd like to make a new IPython file, you're more than welcome to, kind of following the process I did. But now we're going to kind of dive into integrating this name into our code file. All right, so we have our import statements. I think what I'm going to do is make a whole separate code block just to process our national name CSV file. It's not too expansive of a file, as in there's like not too many variables, but there is a lot of information. So I'm just going to have right here, we're going to have our national data set, and we're going to have that be equal to pandas.read CSV, and we're going to be reading national names.csv. And then after that, I just want to print out national data set. We're just going to be printing out the head to make sure that we're processing everything correctly before we actually start cleaning things. All right. It's buffering. It's connecting to the kernel. Okay. We have an error. Pandas is not defined. Oh, because I didn't run the code file from earlier. Okay. Because I made it into part 2. That would make sense. All right. So now I'm going to run this again. I think this should work now. Okay, here we go. So we're having, we have our ID, our name, our year, as far as the gender and count. I think that we're all good to go. So everything looks good. I'm going to start dropping a few variables from our code though. And you can do this pretty easily in pandas. So in order to drop a specific variable from pandas, you just need to use the drop with the specific column. So you'll do the label. So you're going to have, let's see. We're going to have national data set. We're going to do drop. And I want to do, let's do columns equal to ID. And then I want to print out the head once more and see if this is working. All right, no, it's not. Okay. Let's see what syntax I'm messing up, if I can. I don't want to open any files. So escape. Okay. Let's see what I'm actually doing. Seems I have forgotten the syntax. Oh, okay. It looks like I need to add the in place argument. So it actually will drop everything. So it's returning. So I don't need to reassign it. All right. So that fixed it. GitHub Copilot essentially told me that it does not modify the data frame. So it's not modifying national data set in place by default. So what it means when it's not modifying the data frame in place by default, it means that it's not going to return a new data frame with the specific columns it dropped. It's not going to change the original data frame. So I did that by altering the in place variable. So now it says in place is equal to true, which means that we're dropping that specific column. The next thing I'm going to drop is I'm going to drop the gender as well. I don't think that's necessarily relevant to just generating a bunch of video game characters. If we want to go back and maybe add gender as one of the characteristics we want to add in for our characters, we could change this later, but I don't think it's necessarily something we need to do right now. So I will have it be dropping gender and set in place equal to true as well. And then I'll have it just print out the head after these two. And it looks like we have all of these good to go. So we just have the name, the year, and the count. So now I think it's time to actually go through and process this data. So I want to kind of combine all of the names. So we're able to go through, and for all the times Mary was named, like the child was named Mary from 1880 through 2014, I want to return the count of that rather than just by year. So I'm going to do this just by essentially adding them up and creating it equal to a new data set. The first thing I'm thinking of as far as how to do this would just be a for loop. I know like it will take a decent amount of time. I'm not thinking of any more memory efficient ways to do this off the top of my head though. So for I as well as row in enumerate national data set if and then we will make a new data set very quickly. That's going to be updated national, and that's going to be equal to a few things. We're just going to have it follow a pretty simple like overall mechanism. We're just going to have it be like name with like a count essentially. So we're able to go through and we'll have, for example, Mary 7065 and like kind of like etc. But for right now, it's just going to be an empty list. All right. So now that we've done this, I'm going to go through and if row name not in updated national, I'm going to, oh no, I clicked shift instead of enter again. Keep doing that. Updated national, we're going to append it's going to be row at index name, and then the count is just going to be row looking at what is the count. Okay. Count elif row name in updated national. We're going to go to updated national at the index of row name, and we're going to add to the count with our current row count. This is what I'm thinking of will work for the syntax off the top of my head. But if we run into errors, we can always go through and have it be more efficient. So now I'm going to just print out updated national, and I'm going to do the first 4 items. All right, we're running into errors. Indices must be integers. Okay. Oh, I see. Okay, so I will have to do, so I think like how we're doing it, maybe just row 0 because it's the first column, and then we'll have count be just 2. I think that will fix it, but if not, we can go through and make some adjustments. So 0, 2, Okay, let's see if this works. Unmatched. Oh, I did add an extra bracket. Okay. Interesting. Let's just have it print updated national. NM. Oh, I see what's happening. Interesting. So looks like our array is just running 3 times at least. And it's returning name with the first index of Mary year as like the first index with A, as well as count is equal. Oh, I see. So it's returning. Okay. I made a mistake somewhere. So we'll have it's returning the first index, and so at index 0 as well as index 2 for all of these. So we need to fix that basically. All right, so I'm going to Control Z and go back because I think my last attempt was a little bit closer to the syntax we needed. All right, and let's see what error we were getting here. String indices must be integers. So I'm going to go right here and just do Command I, explain with this, so we can see if we can find an explanation from Copilot before I head to Stack Overflow. Okay. It arose. Okay. This might be what I'm looking for rather than enumerate, because it's not necessarily a list. It is it's a data frame. Okay. So I'm going to try this out and I'll explain what essentially is going on while I'm typing everything out. So I asked GitHub Copilot what was going on, and it said that if I'm iterating over the rows of a data frame, I would be doing so incorrectly. If I'm doing it like this, it's going to be, because this is a list rather than a data frame, this is going to iterate over every single row, and we're going to get the index and the row item. So I'd be able to kind of like manipulate them in the way I was initially doing so with the syntax. So I'm going to run this and see how it runs. So we have our first 2 printing out. Seems like it's actually iterating through the entirety of our file, so it's going to take a little while, and we'll see what comes out. All right, it's thinking. In the meantime, I'll look and see if there's any questions. Doesn't look like there's any questions so far. If anyone has any questions about what I've been doing so far, feel free to drop them in the chat, and I'd be more than happy to answer them. may have made an error with how long this file is. Yes, okay. For loop was definitely not the way to go for a 1.8 million line file. So in the meantime, I'm going to start researching more memory efficient ways to do this. Looks like we started getting, nope. Yes. All right. So we're going to look at a more memory efficient way to do this. As far as like what I'm brainstorming immediately, I'm going to make a little just markdown file for me to write down my thoughts. I think a first option would be to just use specific years. And I also think if we maybe snipped it a little bit, so we're not like maybe we use like a decade or something, as well as I can maybe be splicing the data in half. So I'm going to kill this because it's taking 3 minutes and it's going to take much longer with a 1.8 million line file. I don't know why I thought I should use a for loop to begin with. So we just want to use a more memory efficient use of our data. So in order to update this, we're just going to use the updated national version again. And then I think I just want to splice it so that we're just accessing through my 1880, which would be probably the first like 100-ish. Let's see, we're at 500. Let's see. Yeah. All right. So still like 1,000. Yeah. Okay. So I'm going to do something really quickly to change it. So I'm still going to iterate through the rows, but rather than all this, that will be our name. I'm going to just kind of like exit that. And what I'm going to have it do is that if row year is equal to 1880, first I'm going to check the data type. So we're going to print national data set at index 1, and we're going to print off the year. I want to see the data type of this. So here we go. I'm just going to comment these out for the time being so we can get a little bit more information on this. Print. All right. We'll just use another number. So we'll do 2, I think. Or no. It'll be 1. Another error. Key error. Okay. A list by key. So we need to be using just going to do year. Okay, so it is an integer. We're good to go. I just was doing them a little bit out of order. So I'm going to comment this out, comment this back in. So if the row, if the particular item is equal to 1880, I'm going to append it to updated national. So we're just going to have all the items from 1880. We're going to append, and we're going to append row, and we're going to append the name as well as row count. And then else, we're just going to break it. So then after the first few thousand iterations, we're just done. And then I'm going to print off the updated national. Running there. Okay. List has no attribute head. I'll just do the first 4 items. All right. So here we have Mary, Minnie, Bertha, Ella, Laura. Okay. It looks like it's working. All right. So I'm just going to print out the entirety of updated national so we can kind of see how this is looking. All right. Awesome. So now we have a little bit more of a comprehensive data set. It's not quite as big as the entirety of our data set. I just want to focus a little bit more on updating our model and working on the age generation model rather than working through data processing. In this stream, if we have extra time towards the end of stream 3, we might come back to this and add in all of the names rather than just the ones from 1880. So now we have updated national. I'm going to make a little comment right here that says commented out code for use if we have additional debugging time to add in all names from 1880 through 2014. And then here, I'm going to go through and comment what I'm doing here so it's a little bit more readable of code. So I'm going to have reading our national names data set into a value. Data set includes baby names in the US from 1880 through 2014. And here we are verifying our work. We're going to drop irrelevant attributes from our data set. And then again, here we are verifying our work. I'm going to make a few more spaces just so it's a little bit more readable of a code block. And here we have declaring new list to store our names from the national data set that have been parsed /clean. All right, and then we have our for loop, and what we're doing in this particular one is we are adding all baby names and the number of times they appeared from 1880 to our updated national list. And this is just us checking the data type of the year characteristic. Okay, I think that's enough comments for now. This has all been run. So now it's time to actually integrate this particular data set into our model from yesterday. So we're going to do this by coming down to our code block from yesterday. Here we have our character names from yesterday. And I think that we can integrate those like just by joining all of our character names that are from the baby names list. So first, to kind of do this a little simply, I'm going to run one more item. So I'm going to do a just names list. So we'll have one where we can weight the names as well as just the names themselves. So just names dot append row at the name index. Let's see, let's print it out. No errors. So I'm just going to change this variable right here from characters names, and I'm going to put in, instead of characters names, I'm just going to have it be the just names variable. So this is all of the names from 1880. And I'm going to parse through our data set to see if we're using the characters names at all throughout this code block. Character names, if I can type right. Okay, so here, I'm going to change this from character names to just names. And then it doesn't look like it's used anywhere else in our model. So I'm going to be commenting out the original character names block for both of them. And I'm going to run this and see if we run into any issues with regenerating the model. All right, it's thinking. All right, so looks like it's running well. I'm going to actually start generating some names now. All right, we have Will. As you can see here, something that is a little quirk we didn't have yesterday is we're getting random capitalized letters in the middle of our names. This is an issue I ran into when I was like first building out this code in preparation for this stream session, or like the overall like stream series. But I fixed because in our list originally, we had all these character names lowercase, and I did that on purpose that we wouldn't have any weird uppercase letters. But in this case down here, we are having weird uppercase letters because we're training it on a data set where there are uppercase letters to begin with our name. So we can fix that by a little bit of character manipulation. So I'm just going to do that simply by seed dot, it's going to let me type, to lower, I think it is in Python. We just did lower. Oh no, that's JavaScript. I get the syntax a little confused sometimes. Let's try just lower and see if that works. We'll run it again, see if we get any errors. We are getting some errors. Lower is not defined. I'm going to have GitHub Copilot tell me what the actual syntax is because I don't want to go look it up right now. Okay, so it is dot lower like I had originally anticipated. So I'm just going to say accept. I changed it to that. I'm going to run it again. And here we see it is returning correctly. Oh, it got rid of all of our code that we did last time. So I'm going to control yes, and then just do what it said so that we don't lose all of the code that generates our name. Okay, run. Here we have Crowy, Chewy, Chemo. All right. I think these are some more unique names and also a little bit more realistic as names now that we have like a few thousand data set points from the 1880s baby names. I think that's cool. I'm going to just do a simple C and see what it starts to come up with. All right. All right. Some of these are just like plain words, but I do think that a good amount of these are like actual names or names that like we would see like maybe in a video game as well that are typically more creative and like the I don't know, most popular baby names. Although I think that we do add some creativity by using the 1880s specific data set because I don't think very many people are named Thaddeus anymore. So it adds a little bit more diversity of names to our generator. So this is pretty cool. I think that we've updated our baby names generator pretty well. The next thing I'm going to move on to is age generation. So that's like our next model we're going to be building on, as well as characteristic generation. We'll eventually be using OpenAI's API to generate images of our character, but I'm not sure if we'll get all the way through that before the end of this stream, but we do have another session this evening. So I'm going to make a new code block, and this is where we're going to be doing our character age generation. This is going to be a slightly similar process. We're just going to be using LSTM rather than a GRU model for this particular model. So I'm going to start off by importing a few new aspects from TensorFlow. So we'll do our imports. And here we're going to import from TensorFlow .keras, dot layers, import the input function, as well as our concat, innate, and our reshape functions. So these are specific to LSTM, and we'll be using those in a second. In addition, we'll also need to be importing, I think, model maybe? Yes, we didn't import model earlier, so we'll need to be importing the TensorFlow model specific function, and that is in TensorFlow keras models import model. And this needs to be keras, not teras. I made a little typo. So we'll run this. Looks like everything's good to go. I'm going to make a new code block so we're not importing these every single time when we rerun our model. I don't think that's super, super conducive to what we're looking to do. So the first thing we're going to do is create the input layer for our age. So I'll do that by simply create input layer for age. It's just going to be equal to input underscore age. And we're going to set that equal to something that we're using from our input function that we just imported. So inside of that input, we need to declare a shape, which since it's a number, it's going to be pretty simple. It's just going to be equal to shape is equal to 1, essentially, for that comma. That allows for an additional output. And then we're going to be naming this just input age. Simply enough. There's nothing really else we need to do for that. So now we're going to start embedding layers and defining the input and defining the common embedding dimension as well. So I'm going to embed our age. So we're going to embed these layers for our age using our embedding function. So we were going to declare that to the variable of embedding age. Embedding underscore age, and we'll be using our embedding function. And inside of our embedding function, we need to give it a little bit of information. And for our input dimensions, this is the number of vectors we'll be using in our input. We're going to set input underscore dim. This is going to be equal to our input, the shape of our input, but we're just going to be using the first aspect because it's just the age rather than the entirety of our name with like a lot more information needed. And after that, we're going to have the output vector needed as well. So we'll have output dim, and we're going to set output dim equal to the embedding that we've already set. It's the embedding vector we've set. Embedding dim. And we also want to add a little bit of more information. We're going to be multiplying it by our input age. All right, let's run this code, make sure we're not running into any errors so far, and then we can get on our merry way to finish out our model generation. All right, looks like there's no errors so far. I'm going to check for any questions real quick. Looks like there's no questions. Looks like Marcos is having some chai, so I hope you're enjoying that. But let's go on with our model real quick. All right, so now that we have our input layers defined, we have our embedding layers defined as well. We need to actually reshape these embeddings in order to concatenate and define these different models. So we are going to reshape this embedding real quick. We're going to reshape our embedding. After we reshape, we're going to move on to the GRO based generation. And we're finally going to actually compile our model. Compile model and test our model. All right. So in order to reshape our embedding, what we're going to do is we're just going to overwrite our embedding age variable. And we're going to use the reshape function that we imported from TensorFlow. And we're going to reshape it to 1, -1. So it's going to be uniform with a few other of our variables that we'll be using later when we have some additional information for our appearance generation model. So we will have 1, -1 as our first piece of information. And then we're going to be multiplying that by our embedding age. We'll have embedding age. This is just going to reshape it with our reshaping model. Okay. Then after that, what we'll need to do is actually define our GRU output for our model. So I'm going to define the GRU based model. We'll do this by setting model equal to model. And we're going to use a few inputs. We're going to use inputs will be equal to our input for our age as well as our input for our name, input age, and input name. So I'm going to kind of combine the input age and input name in just a second. So this is not declared yet, but it will be in a second. And then in addition to that, what we're going to need to do is set some outputs. All right. And then in order to compile our model, we're going to be using some similar verbiage from the last time we built our model for name generation. We're going to be using the Atom Optimizer again, as well as for our loss, we'll be using categorical cross entropy. All right, and for testing, we'll just need to run model.test. I'm going to pull this out and just see if we have any issues so far, but I don't think we will. Okay, looks like we have a few issues. All right. Okay. Tuple object is not callable. This is line 8. All right. Embedding age. All right. No. Let's see what I did here real quick. For embedding age, I need to have this. So we have our input is set equal to x, shape at index 0. We have our output vector is equal to the embedding dim We have our input age. All right. Interesting. And then, oh, but it's not calling it specifically for that one. It's calling it for when I'm reshaping it. Okay. I was looking at the wrong one. When I'm reshaping it, let's see. Reshape 1, -1. And then I have the embedding age. Oh, I think I see what I did here. There we go. Okay, so that is the first error. Oh, but now it's giving me, takes 2 positional arguments, but 3 were given. Okay, let's investigate this a little bit more. So we have our embedding age, and we're using, all right. No, okay, I'm seeing what's going on now. Okay, so Control Z, I'll be explaining this in a second. I need to close this. There we go, okay. Because we're reshaping it and we're using this as the first argument. Okay, yeah. Perfect. Output is not defined. Okay, that is something I do need to fix. We need to define our output. So how we'll define our output is relatively simple. We'll be using our dense function that we imported earlier with our TensorFlow. So this is just going to be equal to output. No, output is equal to dense. And instead of dense, we need to add a few arguments. So we're going to first add the length of our char to index variable. And after that, what we're going to need to do is use the activation of softmax. Softmax. I'm going to run this. All right. Could not interpret activation function identifier. Softmax. That's because it doesn't have a dash, so that would make sense. It's not actually finding a name. All right. Unrecognized type for outputs. Interesting. All right, let me look through my preparation code from before the stream and see what I'm missing. All right, so we have our input age. All right, we have our embedding layer. All right. Okay, I think what I did initially was combine the age and the appearance layers inside of a single model for our character. I think I'm going to try doing that here. I initially wanted to do just age at first and then our character appearance after the fact, but I think it might be useful to have both of them at once. All right, so I'm going to do something similar. So we'll have our input for our character appearance. We'll have input, appearance. It's going to be equal to the input function. Our shape is going to be similar. We're also going to have this particular shape for our input appearance, and the name will be equal to input appearance. And I think for this particular model, all we're doing is just literally generating the color of their hair. So we honestly could just change it to input hair color, and then I'll change it to input hair color. All right, so now that we have that, I'm going to go down to the embedding layer. and look at what we have here. All right, we have our age. I do think we'll need to embed this as well. Hair color is equal to the embedding layer at input dim. And this is going to be also equal to this. It's kind of very similar, except we're just going to have the initial variable of this rather than age. All right, that looks good. We'll need to reshape it. So pretty quickly, we'll just do reshaping for our hair color. And then we're going to be reshaping, embedding hair color. All right. Okay. Perfect. Embedding. Cool. Okay. Awesome. We do need our common embedding. So this is going to be the common embedding dimension that we talked about earlier. I'll be adding this in. We are defining our output. Okay, and we will need to work on our GRU based output as well. So we're just going to do GRU output. And that is going to be equal to a function that we imported from TensorFlow and we used for our name generation, which is going to be GRU. And we'll be using 128 as far as how many vectors. We're going to return all of our sequences. So we're going to set return sequence equal to true. And then we will be multiplying it by our concatenated embeddings. Which I need to actually concatenate the embeddings. So here we need to concat embeddings. That is going to be equal to the concatenate function that we imported earlier, and we will be calling in an access of 1. And then after the access of 1, we're going to multiply it by a few things, which are going to be tuple that has an array of our embedding age, as well as our embedding hair color. All right, I think that covers everything. And I'm going to run it and see if we have any errors. We do. Let's see what we need to fix now. Unrecognized type for outputs. Model. Output types is equal to output. So we have dense. Oh, I don't even need to be multiplying this by GRU outputs. Okay. One less error. Functional object has no attribute test. That would make sense because we should not be running test. We should be running compile because we're not quite testing it yet. But we're doing that up here. Okay. I think I just, I see what I did. Okay. We just need a summary here. Cool. All right, here we go. We don't have any more errors. We worked through all of our errors and we're getting a summary of our model as being outputted right here. So Here we have all of our layers. We have our input age, input hair color, our embeddings, as well as us reshaping it. There are quite a few parameters. All of them are trainable. So I think it's running pretty well. So now we need to actually call our function. So we're able to use all of this to generate our random ages. So we're going to start by doing that pretty similarly to last time. If you remember up here, we were utilizing our model and looping through using the different probabilities that we're using in our layers. We're going to be doing something similar for age and appearance. Yes. All right. So code. We're going to import a few things if we haven't already. I don't remember if we imported random. Did we import random? Random. No, I don't think we did outside of NumPy. I think we're good to go then. I don't think we need any imports, but calling model to generate our characters' ages. All right, so let's get started with calling all the characters' ages. So I'm going to give it a few different samples to generate some random ages. So we'll start off pretty small to generate these random ages. We're going to give it about 5 samples for right now, just as we're running a little bit close to time. So number of samples is going to be equal to 5. And our sample ages, we're just going to choose some sample ages from the ages of 18 to 25, or not 18 to 25, let's do 18 to 30. So sample ages will be equal to numpy.random, and we'll be choosing a random integer from 18 to 30. And we also want to make sure that we are using, we're finding sample ages in the size that's accurate to the number of samples we want. So after we do this, we will do size is equal to number of samples. Next thing we're going to do is print some of our sample ages. All right, so here we have some of our sample ages. And then we're going to go through and actually call our different random ages in a second for, like now that we have a few kind of like sample ones we're feeding into it. All right. All right. So here we are going to have our appearances generator. And this is where we're going to have our hair color. So have our hair colors are going to be equal to, let's say, blonde, brown, red, black. And we can do like a few fun hair colors as well, like blue and purple, and then yeah, I think that should be good. Next thing we're going to do is we're going to create our seed for this particular variable. This one's going to be a little bit more complicated than our name one. This seed is going to have a random choice of our different names, and then we're going to be assigning it to this. All right, so we'll have seed is equal to NP, which is NumPy, and then we'll be going to random choice, and from that we'll be choosing something from our character names. It's going to be our just names. Okay. We're going to choose a random name as like our seed. We'll be creating everything from our particular probability. Seed index is going to be equal to all right. And then we're going to go through a quick little for loop of our maximum length. So for have our predicted probability and we're going to access it by going to model predict, and we're going to be going into our sample ages as well as our appearances. This is going to be predicting all three of them at the same time. We'll have our model be predicting our NumPy array as well as sample ages at the index of our particular item. We'll also be asking for the NumPy array at seed index as well as sample appearances. So I'm going to bring this in from my prep work, and I can kind of walk you through this. So this is the predicted probability. We're setting that equal to the model predicting a sample age, a sample index of a name. So we'll have a sample age, sample name, and our sample appearance. But this needs to be changed to sample hair color, I think. Yeah. Then after that, we're going to go through and pick the last one for our predicted probabilities. Just going to set equal to predicted probabilities at the last index. And then we're going to go through and actually add something to our next character. Have next character is going to be equal to a random choice based on our probability. So NumPy random dot, and then we will be using choice function as well. And then within that, we're going to go into our list of our different keys. And we will access the keys. And then after that, we're going to go on to our predicted probability. That's going to be our P is equal to predicted probabilities. Looks like that's slightly too far out. All right, let's run this. All right, sample hair color is not defined. All right. All right. Oh, I will have this. All right. So now we're running into some actual errors. Invalid D-type string 19. Which line is it coming from? Oh, 16. Seed index for char and seed. Let's see. Char index, char to index. All right. And these are all being tokenized up here. I'm not sure what the issue is quite yet. Okay. All right. So I'm going to go ahead, ignore this error for the time being, and move on to the rest of the model generation, just to write out the rest of the code for y'all before we get to the end of this session. And then we'll make some to-dos for our part 3 of this session, which will include this debugging. So after we declare the next character for our name, we also need to generate our appearance. So we're going to go to generated hair color, and we're going to set that equal to our next character. We're going to add on our next character. So similar to like how our name generation was working, and we'll also be appending another character to our seed index. Seed index will be appending on our at the char index, next char. And then after that, we're going to append on our sample appearance with our generated appearance, as well as printing out our sample appearance. So here, outside of the for loop, we're just going to have sample appearance, sample hair color. We're going to append our generated hair color, and then we will print out our sample appearance, which is going to return an error right now, but we're not going to worry about that right now. All right. I'm going to print this off. All right. We're getting a few errors. First one is string type, and I'm sure there's going to be a few errors down here with the overall hair like color generator, as well as like the name generator. I'm kind of combining the two here. But for right now, since we have about 10 minutes left before the end of this series in the stream, I'm going to make a quick to-do list to kind of show y'all what we'll be doing in part 3. So part 1 and part 2, we've done a little bit of an explanation of neural networks, as well as gated recurrent units and long short-term memory. The first part, we went through and coded a name generation model. And in this part, we've been working through an age and hair color appearance generating model, as well as integrating a little bit more complexity into our initial model. So here, we're going to have our to-do list for part 3. I'm going to copy over part 2. So I will, actually, we're just going to make a README real quick. We'll do new file. It's going to be part 3 to-do.md. So here we have our to-do list. So what we're going to be doing is we are going to be debugging our age and hair color model. And then after we have successfully debugged that and we're generating our age and our hair color, we're going to input our information into the OpenAI API to generate an image of our character. And then for our reach to-dos, what we'll be doing is we will be integrating more name data from our national names data sets. All right, so I'm going to save that, and then we can, let's see, look at this side by side. Here's a little preview of the to-do list, so you have a little bit of an idea of what we'll be doing in part 3. We have someone asking how I am. I'm doing all right. A little bit frustrated by the bugs, but we'll figure it out as we go through part 3. Right now, we're learning about recurrent neural networks. I gave a little bit of a conceptual application or conceptual explanation at the beginning of this workshop. And now we've kind of dove into building our own recurrent neural networks, specifically using gated recurrent units. Here's our to-do list as far as like what we'll be doing in part 3, which will be tonight at, I think, 7 p.m. Eastern. Let me verify that on the Global Hack Week site. Yes, so part 3, our last part of game world building, will be at 7 p.m. Eastern, which is, I don't know what time it is in IST. It is 4:30 a.m. IST. It's a little bit early in the morning, but if you'd like to join, and if you need to convert the workshop to your local time, you can do so at this link. It'll just show up in like whatever time zone your computer is in. We'll be at that time debugging our age and hair color generator model, give y'all a little bit of a break as well as myself to think about it a little bit more. We'll be using the OpenAI API, specifically the DALL-E function, to generate an image of our character. And then hopefully we'll be integrating some more name data into our national names data set, but we may not have time for that. In the meantime, if you'd like to check out the code I was working on, this is the link where you'll be able to access it. I'll push it after I get off the stream, and you'll be able to access all of the part 2 data in addition to part 1. That's all in there, and it'll be labeled in the IPython files. And the data set that we're using is uploaded to there. I'll add a little bit more context towards the end about which specific Kaggle set that is. But if you want to look out for it, you can do so with this bit.ly link. I sent it earlier in the chat if you'd like to access it. We already did this. Thank you for coming along to part 2 of game world building using recurrent neural networks. If you have any questions, feel free to pop them in the chat. If you'd like to access the slides or go back to my explanation of gated recurrent units or long short-term memory, you can do so by accessing the bit.ly link on the screen. This will be a link to the slides, and I'll put that in the chat as well. But thank you all for coming out, and I hope to see you for part 3 this evening. Awesome. Looks like we have some happy hackers. Glad to hear it. I hope y'all were able to learn something and were able to fix the bug this evening. It's really cool and interesting models to me, and I'll be excited to work with OpenAI API for a little bit as well at the end. Awesome. I'll see y'all tonight at 7 p.m. Eastern. See you in a few. Happy hacking in the meantime, though.